event-driven architecture. And most of us are probably thinking that this is one specific way of designing your microservices in your backend. And it turns out that it's actually not. First of all, it's a bigger concept. That includes many smaller concepts related to it. And second of all, I would say most importantly, it includes specific design patterns for designing your microservices within the system that then make up this whole event-driven architecture. In this video, I want to talk about first use cases for event-driven architecture, because this isn't essential. There are cases when you don't want to use event-driven architecture, and there are cases where you want to use. It always has pros and cons, so it's important to know them. And then we're going to dive a bit deeper into different design patterns for event-driven architecture. As you can see here, we're going to talk about event notification, event carried state transfer, event sourcing, and CQRS. And of course, we're going to talk about next steps. We're going to also look into common technology that is used with event-driven architecture. And we're also going to look at some code, some basic code. And I think this is going to be fun. So if you're ready, let's get started. So as you can see, this is the basic diagram for an event-driven architecture. First thing that I want you to understand, this is different from a traditional way of microservices querying. So one microservice, let's say this one, querying another microservice to fetch some data. As soon as the data is fetched here, this microservice can then proceed querying or sending the data to the database, maybe to another service. This is a bit different with event-driven architecture. The event-driven architecture is literally the embodiment of the pattern called publish-subscribe pattern, where you have a publisher. So one service is going to act as a publisher, and it can have one or more subscribers that are waiting for this event and then consuming this event and doing something with it. One cool thing about this one is that publisher actually doesn't have to know about its subscribers. So publisher will literally just publish the event and not know about what the subscribers are and what the subscriber is going to do. Actually, this is very similar to another design pattern called the observer pattern. And I also have a couple of videos on design patterns, so check them out. It's different because that in the observer pattern, observable knows about the observers. In this case, it doesn't. So if we go back here, we're going to see that the event A publishes an event to a message broker or event broker. So event message broker is basically a queue that gets piled up with different types of events. And then services like B and C are subscribed to this queue. And then they're going to see that, hey, there's a new event, and they're going to consume it. So it's going to go to the event service directly, and then is going to be processed in one or different ways. Now, here is one cool thing. So if we wouldn't have used the event-driven architecture here, service A would have contacted service B directly, and then, of course, waited for an answer maybe, and then service C separately. But in this case, service B and C are kind of unknown to service A. Service A is only concerned about publishing this event. And then, based on the technology, service A can already be sure that whoever listens to it is going to do something useful with this event. All right. So what are the benefits of this kind of architecture? First of all, high decoupling. High decoupling in the sense that service A doesn't know about service B or C, and service B doesn't know about service A or C. The only thing that it knows is that, hey, there's an event that I can listen to and then pick up. So you can actually scale service B as much as you can, depending on how much operations you do here. You can also scale service C or A. And another cool thing is that the event is going to be consumed as soon as possible. So it's very fast, meaning that service A doesn't send a request to service C or B. It's only sending the event to the event broker or message broker, and then it's consumed as soon as possible. So it's kind of faster when you have to deal with different components compared to the traditional way. So the use cases for this you probably already guessed them, will be real-time notifications. For example, you load your Facebook or Instagram and you have some followers, some new likes from other people. So let's depict that. Let's say you have a phone and you open Instagram, and here's the server of Instagram. So instead of loading your phone and then polling, you probably know what polling is. If not, polling is fetching the data continuously. So let's say every 5 seconds, we try to fetch our likes. So whoever liked our post every 5 seconds to kind of refresh the number of likes in our Instagram profile. But this is kind of adding too much processing burden, or this is a burden for our phone because it has to do this operation internally every time. So in the event-driven architecture, we're only going to subscribe to a specific broker, let's say here, and our servers is going to asynchronously add these events. Let's say, hey, 1 like came in, another like came in, 3rd like came in, and then we can display them within the app. So real-time notifications, very useful. A live chat. So whenever you're in a Discord server, somebody sends a message, let's say person A, instead of service A, person A sends a message, and then this is basically where the messages get stored, and then everyone can actually see this message because they're subscribed to this server. All right. The third one will be logging. For example, if you have some kind of a logging application within your organization, and different logs security logs have to go to service B, some other logs, just warning logs, should go to service C, and this is how you can segregate your logs pretty much. It can be used for caching and multiplayer games. Imagine one person is playing the game and they publish the event to the message broker, and other players have to see this event in real time. So they're not going to obviously make requests from the game to the server all the time. They're only subscribed and they're simply getting these events, and this is being rendered real time within the game. This is actually how multiplayer games work. So now let's go further and actually discuss the first pattern called event notification. This is one of the most common patterns, and most of us actually usually think about exactly this pattern when we hear event-driven architecture. So what is actually about? This is about a user. Let's say, imagine this is an e-commerce website. This is Amazon. It can be something similar. The user orders something. The user makes a purchase, so our request is going to go to order service. Actually, let me change the color to red so that it's easier. The order service is responsible for processing this whole thing. This is kind of the main microservice within our e-commerce platform. So this is going to be a synchronous call, like a direct HTTP call. All right, maybe not synchronous, but it's an HTTP call. Then order service has to fulfill the payment. All right, it has to make the payment. Maybe payment service is like a Stripe. So let's say this is Stripe, and Stripe is going to process our message again asynchronously, but it's also another HTTP call. So we make the HTTP call to make sure that the payment succeeded rather. And after we have that, then we can kind of publish an event to the broker. We're going to publish this event called payment succeeded. And then first, there are 2 things that we want to be fulfilled after the payment has succeeded, or rather 3 things. First of all, we want to update the inventory, meaning now we have 1 less item in our inventory. So if we have 2 items, people cannot buy more than 2, and we want to show this in the website. And also we want to send a confirmation email to the user that bought the item. And third one is that we want to actually redirect the user from like the waiting page to the purchase succeeded page. All right. So what's going to happen is that, so you see this green line, as you saw previously, this is publishing. So the order service is simply going to publish an event to the event broker and forget. Really, the order service is not doing anything anymore. Now, these independent services are going to listen to this event, and we're going to update the inventory first. Second of all, we're going to send an email to the user. And third, we're going to redirect the user to the purchase completed. Now, these three things, all these three operations, this 1, 2, and 3, are going to happen simultaneously. They're going to happen at the same time. All right. This saves us a lot of time. So we don't have to wait for this one, and then do this. We can do all three at the same time. This is actually one of the biggest ways of using event-driven architecture or messaging rather within your app. Now you can actually ask, what if one of these fail? All right. In a distributed system, everything can fail. It can be a network failure. It can be an exception. Everything can fail. What are you going to do? Well, there are some remedies for that. Okay, there are some things that we can counteract. As always, everything can fail, and also in event-driven architecture. But the main purpose here is that you can see a lot of decoupling and actually speeding up of all the processes. So this is definitely pro rather. Now let's look at the actual pros and cons here. So pro, high decoupling, as I said. Asynchronous task handling, again, all these three components handled their processes asynchronously. Increased reliability because, okay, we are using a message broker, and if you send an event here to the message broker, you know that it's either going to be stuck there or it's going to be processed. So if an inventory service picks up the event and tries to process it, update the event, then it already picked it up. If it didn't have time for some reason, maybe it was down, the event is simply going to sit here and wait for the inventory service to, again, boot up and connect to consume this event. So there are two cases. Either this event stays in the queue, never gets flushed, so to say, or acknowledged, or it is being acknowledged. Okay, two cases. If it is acknowledged, of course, we can make a request to the database to update the inventory, and it can fail. Then we have to go to the corresponding service and actually debug it. This has nothing to do with the event-driven architecture. But there's also one more case. One more case is that for some reason there was an error when consuming this event. So whenever an event is consumed, usually the subscriber is going to send an acknowledgement called ACK. All right, this signifies that the event can be now deleted from the queue and like nothing happened. But there are some cases when there was an error and now we're going to send an ACK. When we send an ACK, the event is simply not going to be deleted from the queue. Sorry, but I lied. There's even one more case. One more case when the event stayed for so long in the queue that it simply never got consumed. And you can configure it within, let's say, RabbitMQ, one of the message brokers. You can configure this policy, and then if the message hasn't been consumed within, let's say, the next 5 minutes, it's going to end up in a dead letter queue. All right. Dead letter queue is something like this. It's literally one of the, imagine there's another message or another queue where all the events that never got processed end up. And then a human being, a developer, can actually look into it and see, hey, this event never got processed. What is it related to? Oh, it's related to this purchase ID. And then you can manually go and maybe contact the customer and say, don't worry, we're going to process your purchase manually. All right. So first of all, let's look at RabbitMQ. RabbitMQ is one of the most popular messaging brokers or technologies. You can also use it with Node.js. And the way it's going to be working is basically we have a producer, we have an exchange. In this case, it's a direct exchange. You can also have queues that are kind of connected to an exchange, and then you can separate the queues by topics, so to say. So you can say info, warn, and error events are going to this queue, and the error event is going to this queue separately. So this queue only takes error, and this queue takes all these three, and then you can have separate consumers. If we look at the code, it actually looks very simple. So MQP broker can just run in a separate Docker container. So it's going to be, so this thing here, this yellow thing is a service on its own. All right. This is also a service. It's just that I didn't put the name service. It's going to run on its own service. We're going to connect to it with a local host, and then we can assert that actually in this example where I'm not using an exchange, I'm using a queue directly. So if you look here, the publisher is going to connect to the queue directly because all the queues are listening to the same event. So I'm going to create a channel and I'm going to start the queue that the queue hello exists. And then I'm simply going to send a message to the queue. The message is going to be hello world. All right. And now I have also a consumer, and a consumer very much identical asserts that the queue hello exists. So these two names have to match within publisher and consumer so that they can be connected. And then I'm going to consume the event. And as soon as the event is received, I'm going to print it out. If you want to see me actually doing some videos on RabbitMQ, which I'm probably going to do, then subscribe and tell me in the comments if I should dig deeper in the code and into real world examples here. All right, going back to our Blackboard. So we got to finish the cons. So another pro is that setting up retry queues. So as I said, these events can end up in a dead letter queue. Dead letter queue or exchange looks like this, and they're going to end up in this dead letter queue. All right, the events that never got consumed. But you can also configure a retry. So let's say if this event never got consumed by anything, the RabbitMQ is going to pull it out and then push it again so that the subscribers can maybe react to it this time. Okay, now the cons. High decoupling. High decoupling is also in the pro and also in the con. So high decoupling has its own advantages, like scaling, first of all, but it also brings some disadvantages. Now the order service never knows whether this event is going to be consumed or not. So this means that whenever you're trying to debug this issue, if there's an issue with your order as a developer, you have to maybe look into every microservice separately. So it's obviously easier if you have one microservice doing everything compared to 3 different microservices doing 3 different things in a decoupled way. So you'll probably have a bigger area of debugging, all right? But this is kind of a given with microservices. And implementation overhead. You have to learn event-driven architecture. And probably you are if you're watching this video, so congrats to you. Now, going further, there's one differentiation between tasks and events. So obviously, all these events that are being published are events, but it's good to differentiate between them because based on one, it basically contributes to a clean architecture. There can be an event that is a task, let's say run cleanup, which literally tells the services, hey, run, do something, and then service is going to react on it. But it can also say something like just an event, payment succeeded, and you kind of fire and forget, and then somebody has to react on this event. So this is just a naming convention. This doesn't really affect any operations. This is just a naming convention to make your architecture even cleaner so that you see the purpose of each event, or rather a task. So if it's an event, then, oh, actually this one has to go here. So tasks in the blue one represent actions. For example, sending an email asynchronously or inviting a person. And then when this happens, usually it's targeted to one specific microservice, all right? Like send an event. So we know that, all right, this task or this event will always go to this emailing a microservice. Compared to events, events are to be considered notifications sent in a distributed way. So usually when you send an event, you know that you will have one or more subscriber waiting or listening to this event, okay? A task knows what action will be performed with the sent message, sent an email, whereas the event doesn't know how its message will be consumed. Its only purpose is to notify, no matter who consumes the message behind it and for what reason. For example, logging. Something happened, and then the logging microservice just picks it up and logs it. Okay, so there's no action. The logging service just wants to log something. If this is clear, then I think we can move to the next pattern called event carrier state transfer. So here's an interesting thing. What this is how an event would look like. All right. So this is how an event look like, and in case of event notification, as we saw in the previous diagrams, when a user, for example, updates their credit card information, you will have this kind of an event fired within your exchange or your event queue with Node.js, for example. This is what you would put. Let's look at the publisher. This is what you would put into the message. Obviously, I put some nonsense, hello world, but this is what JSON file, JSON structure you would put there. And you can see that we have some spec versions and custom ID and so on, and we can also have like a source, meaning what the source of this event was. But we can also extend it and be a bit more specific. For example, we can put a data object and say that, hey, the credit card number is actually this, ending with these 4 numbers. Now going further, sorry, I'm a bit sick, so my voice is weird. Going a bit further, we come to event carried state transfer. And in this case, it's very simple to, it's very similar to the event notification. The only difference is in the data that we include in the message. So in this case, we're also going to capture the differences between what happened before and what happened, what our state looks now. So literally the differences between the old state and new state. That's why it's called event carried state transfer. So we're going to say data and credit card number, but also old state, this, let's say we updated the expiry date, and new state is this, all right? Or we can even go further, make it more specific, and we can put the whole credit card information in the old state and then all the new state, so that these services can receive all the information from the event publisher and then act on it. All right, this is the whole reason behind event-driven architecture. The data is transferred from one place to another, and of course you can decide how much data you want to include. Okay, this is another big pattern within event-driven architecture. Now let's go further. Let's go to event sourcing. This is an interesting one because many people don't understand that, and it can be a bit tricky. So let's go further. Let's say you have one service, let's say order service, and a database connected to it. This is a relational database, as you can see, where we're trying to capture all the orders. And let's say we have 3 orders at the moment. 2 of them are completed and 1 of them is not. 1 of them is pending, all right? So we send a message to PayPal or Stripe to actually pay for this purchase. And then let's say as soon as Stripe replies to us, we want to change this status to completed, okay? Or when the order itself is finished. So what you would usually do in a not event-driven architecture is you would make a query, a SQL query, and update the status to completed, all right? Now, in different domains, such as fintech, for example, in banks, sometimes in e-commerce as well, there are cases where you don't want to overwrite the data that you have. Of course, you don't want to overwrite the data because you want to capture all the events first and know how your data in your database looked like at every point of time when an event happened. So for example, let's say at 12 o'clock, our database looked like this. And then at 12:30, all of them were completed, all right? All 3 orders were completed. Now, if we have some error within our banking system or a customer says, hey, my money disappeared from my account, we want to be able to go back in time and see how our database looked like literally 30 minutes ago. And this is why it's really hard to do this in this way. This is why you need something like event sourcing. So event sourcing is going to have one database that's acting as a source of events, event sourcing, and what it's going to do is simply capture the events. So order created, order completed, and then this first order, this one, is going to be completed after some time. And now what we're going to do is simply create another event and put it on top of the queue. That's it. This is called event sourcing. Okay, not yet. Okay, not event sourcing, but this is the main idea. Okay, now we have captured every state of our database whenever an event happened. And of course, you can tell your database to make snapshots after each event, or maybe let's say after 5 events have happened, you make a snapshot of how your event looked like. Now, you can do this with many technologies. Probably RabbitMQ is not the right one for this, because RabbitMQ is mostly used for messaging, like sending messages from one place to another. It's like as soon as the event is consumed, acknowledged, it just deletes it from the queue. But Event Store, another type of database, is perfect for event sourcing. Apache Kafka is also good for event sourcing, and if you look at the use cases, it says event sourcing there. Now, going back to our Blackboard, what you will see here is that the pros are that it solves one of the key problems in implementing an event-driven architecture and makes it possible to reliably publish events whenever state changes. So event sourcing will use event carry transfer, and it's going to save the state of the data within each event. All right, and you can also create snapshots if you want to be able to roll back and query the data that you have under the pile, so to say. Also, it provides a 100% reliable audit log of the changes made to a business entity. So this is literally an audit log. You can say, I can have this kind of a database and go look into the logs, but it's much more difficult to recreate the state of the database from the logs only. This is much easier with event sourcing. Also, it makes possible to implement temporal queries that determine the state of an entity at any point in time. As I said, there you can make queries to literally retrieve the state, and these queries can be specific, but they can be constructed easily to, let's say, roll back your application or get a snapshot of this, of your state in a temporal way. All right, let's talk about the cons. It's very unfamiliar. It's very new. You probably maybe never heard about this, so there's definitely a learning curve. The event store is difficult to query since it requires typical queries to reconstruct the state of the business, as I said. And it's likely to be complex. And you should probably use the next design pattern that we're going to talk about, which is CQRS, stands for Command Query Responsibility Segregation, to implement queries. This in turn means that applications must handle eventually consistent data. So what is eventual consistency? Also another term used for the fact that if we have 2 databases, and actually let's go further and talk about this here. Or should we talk about this here? Yeah, let's talk about this here. So no, let's actually talk about this here. We have 2 databases. Usually what you do in bigger applications is that you don't use only one database for writing into it and reading, because it can be very slow. You usually have more reads than writes. Just remember all the applications you worked with. You usually have more get HTTP queries than post. So it makes sense to kind of scale the read databases, this one, compared to the write one. So if you write some data to the write database, you need to make sure that they are synchronized. Because what if you literally read the data 1 second later, and if the data that you wrote into the write database is not synchronized in the read database, there's going to be a mismatch. So there are some techniques. For example, whenever you write, you can write into both databases. This is one way. There's another way of setting up a sync job between 2 databases. Also one way. But you can never be sure that it's going to succeed. That's why this is called an eventual consistency. So There will be consistent at some point, but at some point, not immediately. Okay, just keep this concept in mind. This is gonna come in handy. All right, so now let's talk about command query responsibility segregation. So what is this about? As we saw, we have a database for event sourcing, all right? And we make a request and we save all the events in this event database, or how Apache calls it. How does it call it? Yeah, event audit log, event log. So our events are here and they look like this. And let's say you have one service that actually listens to database changes. It listens to the log, and as soon as something's appended, it wants to react on it. Okay, but let's say application has to scale, so we cannot only have one database to query and read from. So we have to scale it a bit. All right. The way we're going to scale is that within the command query responsibility segregation pattern, we are going to resolve back to this scheme, but none of these techniques such as synchronizing the databases or writing to both databases can actually be viable because it's an event-driven architecture. So with an event-driven architecture, you can solve this issue the following way. So the order service is going to publish the event into one database, and usually this can be the event store database, as I showed, or it can be a Kafka. And then this is going to act as our write database. So we're segregating the responsibility. Our queue is a Kafka database or Kafka service. All right. And then our read database can be linked with an upsert service. So Kafka has this magical feature that it can also publish an event, even if it's going to act as our event source. It can also publish an event, and our third service called upsert service is going to listen to this event. As soon as it fetches an event because it's subscribed to it that, hey, we wrote something to the database, this service can also act as a message broker. And now your other services can listen to this event from this upsert service, which is also message broker, and then it can also publish or send a query to the read database. Okay, we're still writing to the read database, but now we're kind of more sure that we have first consumed the event and then wrote to the read database. Okay, there's one more question, which is how can a database or how can a user literally read all these events in a good way? Because let's say I've purchased a lot of stuff in my lifetime from Amazon. All right, I purchased stuff for $2,000. All right, and across the span of many years, let's say one record, second record, and imagine you have hundreds of these records. Whenever I want to see statistics of my purchases, like how much money have I spent, does my database have to go through all these rows and make a sum of this? This might take a lot of time because we have a lot of events in our database. So for this, the read database can actually create materialized views. All right, we're still going to write all the events to the read database, but the database, for example, the Postgres, we can create materialized views, and the way you create it is basically you give it a name and then you give it a query. For example, the query is going to be select everything from, let's say, my tab, and this is basically going to be kind of a cached version of the query that usually the users try to request. And of course, you can create kind of revalidate this cache by, let's say, if there's a new event coming, we will put this to our Postgres database and then refresh the view that we need. You probably already know if you've worked with databases, but this is the way how you can kind of make use of these event snapshots, even if there are too many of these events saved in your source. All right, now let's talk about the pros and cons. Independent scaling. Read and write databases can be scaled independently, as I already said. Optimize data schemas. Write and read sites can use schemas optimized for update query with materialized views. And cons, eventual consistency. You can unfortunately never be sure that these databases are going to be in sync at the point when you need it. So it really has to be a non-mission critical application that you're working on. For example, Amazon. People, for example, maybe in an e-commerce way, getting your shopping cart information can be a bit of a lag. All right, user sees that, okay, my numbers are not matching, refresh the page, now they're matching, nothing bad. But let's say if it's a self-driving car and you need to read the logs from the engine at real time to show it to the user in the cockpit, obviously this is mission critical, so you cannot you have to be more consistent, and you cannot have eventual consistency. Therefore, consistency important in an application. Extra precautions will be needed. All right. So what I want to say is that you don't have to use event sourcing for every case. Even within one platform, within your application, you can have parts where there is no event-driven architecture. For example, here, when we make a request to the payment service, we're not using event-driven architecture. We're doing a normal HTTP call. All right. Now, going back to the cons, separate database increases storage costs. So you have to store the same database, but 2 times, and maybe not 2 times, but still increases the costs. And data synchronization between separate databases, increasing implementation and troubleshooting effort, as you might have expected. Guys, next steps are going to be even diving even deeper and understanding some details of these patterns, and also looking into some edge cases and improvements of the event-driven architecture, which I'm going to explore even more in future videos. I'm going to publish videos on specific details of these so that we are more informed. And also we're going to take a look at the code. So stay tuned, subscribe to the channel, and I'm going to see you guys in the next one. Goodbye.